Continue with chapter 2, that is thyristor. I discussed about what is the structure of thyristor, what is the basic structure of thyristor. Then what are the modes of operation, in how many modes it is operated. Then based on modes of operation, how to draw the static VI characteristics. In 3 modes of operation, what are the observations, all these concepts I discussed. Now in this session, based on this concept, you concentrate some classroom workbook problems, then you go for the another concept. Okay, that we will see the classroom workbook, that is topic 1. This comes under topic 1. Okay, that is construction. This is topic 1. Construction, static VI characteristics and modes of operation of SCR. Concentrate on first question that given in classroom workbook. A DC source of 100 volts supplies a purely inductive load of 0.1 Henry. The controller is an SCR in series with source and load. If the specified latching current is 100 milliampere, then the minimum width of the gating pulse to ensure turn on of SCR would be dash. A DC source of 100 volts supplies purely inductive load. The controller is an SCR in series with the source and load. Now based on the given data, you draw the circuit. In this is the first question given in thyristor concept. An SCR is placed in between source and load. A thyristor is placed in between source and load. A thyristor is placed in between source and load. What the source voltage it is given? How much? Yes, 100 volts. What is the load? 0.1 Henry. Load is 0.1 Henry. Yes, load is 0.1 Henry. This latching current is given as, how much latching current is given? 100 milliampere. Latching current is 100 milliampere. Then to ensure turn on, the minimum width of the gate pulse is dash. Then minimum width of the gate pulse. In this, what is the minimum width of gate pulse? Minimum width of gate pulse. What is the minimum width of the gate pulse? This is the question is asked. The options it is given. A is 10 microseconds. B is 50 microseconds. Option C is given 100 microseconds. Option D is given 1 microsecond. Then tell me, what is the solution for this problem? For reliable turn on, what is the minimum gate pulse width required? Gate pulse width. This is gate pulse width is required. In the concept I discussed, gate pulse width is nothing but a gate on time. What do you mean by gate pulse width? Gate pulse width is nothing but a gate on time. Gate on time. I told already. It is, you want to calculate minimum gate pulse width. For reliable turn on of SCR, gate must be connected up to which current? Latching current. For reliable turn on of SCR, gate must be connected. The current through the SCR must be reaches to latching current. This condition you know. For reliable turn on, gate must be connected. Gate must be connected. Gate must be connected up to which current? Latching current. Up to latching current. Then in this circuit, you find the time corresponding to latching current. To find the time corresponding to latching current, then how to apply the formula? Simple. Here the supply is DC, load is inductance. Then the only formula available is, then you apply the voltage across the inductor is V equal to L into di by dt. But here initial conditions are not given. If the initial conditions also given, you can do like this only. But according to that, you can substitute the initial condition. But in this circuit, they don't give any initial conditions. Then shall you write like this? Di equal to V by L into dt. Na? Then integrate both sides. Integral di equal to V by L into integral dt. Then I equal to V by L into T, some constant K. Then at T equal to 0, at what is I equal to 0? Because we know the property of inductor. Inductor cannot allow the sudden change of current. That's why at T equal to 0, I equal to 0. Then you substitute here this 0, V by L into T plus K. Then what is K equal to 0? If the K equal to 0, then what is I equal to V by L into T? Then corresponding to latching current, if I equal to IL, this time is which time? Minimum gate pulse width. Then what is the minimum gate pulse width? This is the minimum gate pulse width. If substitute I equal to IL, then the time is taken as a minimum gate pulse width. Then what is the minimum gate pulse width? Minimum gate pulse width is equal to IL into L by V. What is IL? It is given latching current 100 milliamperes. 100 into 10 to the power of minus 3. What is L? 0.1 Henry by what is V? 100 volts. Then what is the minimum gate pulse width? T on equal to 10 to the power of minus 4. Shall you write like this? 10 square into 10 power minus 2 into 10 power minus 4. This is write as 100 microseconds. Then what is the minimum gate pulse width for turn on of the SCR? The minimum gate pulse width for turn on of SCR, for reliable turn on of SCR is how many microseconds? 100 microseconds. For first problem, option C is correct. According to given options, option C is correct. So, okay, clear? Then go for second problem. Problem number 2. This model I already given in the examples what I explained during the concept. SCR is conducting and current through SCR is 20 amperes. If the gate current is reduced to 1/4, then the current through the SCR is dash. What the options are given? Option A 5 ampere, option B 20 ampere, option C 4 ampere, option D how much? 80 ampere. What is the answer, you tell me? Yes. SCR is conducting and current through the SCR is 20 amperes. SCR is conducting and current through the SCR is 20 amperes means we know that once the SCR starts the conduction, gate loses its control over the SCR. Na? Once the gate loses its control over the SCR means you can increase the gate current or decrease the gate current. Is there any change of anode current? There is no change of anode current. Then what is the answer for this one? During the conduction of SCR, what the current is given? 20 amperes. Then if you reduce the gate current is 1 by 4, again current is how much? 20 amperes. For question number 2, answer is 20 amperes. That is option B is correct. Option B is correct. Then concentrate question number 3. Concentrate on question number 3. Concentrate on question number 3. Yes. In SCR, latching current is 12 milliampere. Then its holding current is dash. Yes, tell me. In SCR, latching current is 12 milliampere. Then its holding current is dash. Okay. What is the latching current? 12 milliampere. Then what is its holding current? This the question is framed. In the options, what it is given? Option A 8 milliampere. Option B 6 milliampere. Option C 2 milliampere. Option D 12 milliampere. Then what is the solution for this problem? We know that what is the relation between latching current and holding current? One relation is latching current equal to 2 to 3 times of holding current. In average, latching current is equal to 2.5 times of holding current. What the latching current is given? This latching current is how much? 12 milliampere. Then this is 2 to 3 times of holding current. If you take 2 times, then if you take 2 times, what is the holding current? 6 milliampere. If you take 3 times, then what is the holding current? 4 milliampere. If you take 3 times, that is 12 milliampere equal 3 into IH na, then IH equal 12 by 3, 4 milliampere. If you take 2 times, 12 milliampere equal 2 into IH na, then what is IH? 6 milliampere. For example, if you take 2.5 times, then what is the holding current? 4.8 milliampere. Any answer we can get. But only one answer will give in the options. Then which is the correct answer? Then holding current is equal to 6 milliamperes. The answer is framed according to 2 times. Latching current is equal to 2 times of the holding current. We may expect in terms of 3 times, we may expect in terms of 2.5 times, we may expect in terms of 3 times. According to that, we can select the answer. Then see the fourth question. In the same topic, what is the fourth question? The circuit shown in figure, the latching current is 40 milliampere. To ensure reliable turn on, minimum gate pulse width is dash. The circuit shown in figure, the latching current is 40 milliampere. To ensure reliable turn on, minimum gate pulse width is dash. This is the given circuit. This is resistance and it is inductance. What is the resistance given? This is 20 ohms. What the inductance is given? That is 0.02 Henry. 0.02 Henry. The supply voltage is how much? 100 volts. How much latching current is given? 40 milliamps. Then what is the minimum gate pulse width? What is the minimum gate pulse width for reliable turn on? I told the concept. To calculate the minimum gate pulse width for reliable turn on, you calculate the time corresponding to latching current. That gives the minimum gate pulse width for reliable turn on of the SCR. Clear? Now tell me. You want to find the time corresponding to latching current. First, I want to write the expression for current in the circuit. But no need to derive again equation. No need to apply KVL and derive the equation. This is the fundamental concept. RL circuit excited with DC supply. If RL circuit is excited with DC supply, then what is the fundamental formula? I equal to V by R into 1 minus e power minus R by L into T. Then you find this time corresponding to which current? Latching current. I equal to, what is V? 100. What is R? 20 ohms. 1 minus e power minus 20 by, what is L? 0.02 T. Then you find the time corresponding to latching current. 100 by 20. 1 minus e power. How much you get? Minus 1000 T. This time is corresponding to latching current. This time is taken as minimum gate pulse width. Corresponding to latching current, that time is taken as minimum gate pulse width. Okay. Then what the latching current is given? How much latching current is given? 40 milliampere. 40 into 10 to the power of minus 3. This how much? 5 into 1 minus e power minus 1000 T on. Then 1 minus e power minus 1000 T on is equal to 20 into 10 to the power of minus 3. This e power minus 1000 T on is equal to 1 minus 20 into 10 to the power of minus 3. Okay. Take natural logarithm on both sides. Minus 1000 into T on is equal to ln of 1 minus 20 into 10 to the power of minus 3. This, if you simplify this one, what do you get? Minus 8.03 into 10 to the power of minus 3. Then from this, what is the T on we can get? 8.03 microseconds. This T on we can get 8.03 microseconds. This is the minimum gate pulse width. This is minimum gate pulse width. Gate pulse width in the sense minimum gate on time. Minimum, the gate supply must be connected 8 microseconds. Minimum gate pulse width for reliable turn on of SCR. Gate pulse width is nothing but a gate on time. Clear? Just we are calculating the time corresponding to latching current. That gives the minimum gate pulse width for reliable turn on of SCR. So, okay. Then you go for, this is question number 4 and this is the solution. This is the solution for this problem. This is the solution for this problem. So, okay. Now see the question number 5. Concentrate. Go with question number 5. The circuit shown in figure, the latching current is 40 milliampere. To ensure reliable turn on, minimum gate pulse width is dash. The circuit shown in figure, the latching current is 40 milliampere. To ensure reliable turn on, minimum gate pulse width is dash. This is question number 5. Okay. This is the given circuit. Yes. The supply voltage is 100 volts. Yes, the supply is 100 volts. This is 20 ohms. 500 millihenry. And this is 5 kilo ohms. This is I1 and this is I2. Given that latching current is 40 milliampere, then what the minimum gate pulse width for reliable turn on of the SC? Again same concept. To find the minimum gate pulse width for reliable turn on of the SCR, then you find the time corresponding to latching current. That in this circuit, the latching current is IL. Then how to write IL equal to, you concentrate, IL equal to I1 plus I2. I1 is the current passing through the RL circuit with DC excitation. I2 is the current passing through the resistance with DC excitation. Then for this, how to write the formula, you know. If it is excited with RL circuit, that means RL circuit is excited with DC supply, means how to write? V by R, that is 100 by R is how much? 20. 1 minus e power minus R by L. R is how much? 20. L is 500 millihenry into T plus. This is excited with DC supply R circuit na, that is 100 by 5 kilo ohms, 5 into 10 cube. So okay. Then what the latching current you tell? Then latching current IL equal to, latching current IL equal to this 100 by 20, 5. 1 minus, what you get, you tell me? That is 0.5 now, that is minus 40 T. E power minus 40. This time is taken as a gate on time. Corresponding to latching current, this time is taken as a minimum gate pulse width. This how much? 20 into 10 to the power of minus 3. This is 40 into 10 to the power of minus 3 now, 40 milliampere. That is 5 into 1 minus, this is e power minus 40 T on plus this is 40 T on. This is equal to how much? Plus 20 into 10 to the power of minus 3. As 1 minus e power minus 40 T on is equal to 20 into 10 to the power of minus 3. Yes, how much you get? E power minus 40 into T on is equal to 1 minus 20 into 10 to the power of minus 3. Clear? Then take natural logarithm on both sides. Then what you get? Minus 40 into T on is equal to ln of 1 minus 20 into 10 to the power of minus 3. Then you calculate what the minimum gate pulse width means. Minus 40 into T on is equal to minus 4 into 10 to the power of minus 3. Then from this, what is T on? The T on equal to 0.1 millisecond. This is the minimum gate pulse width for reliable turn on. This natural logarithm we calculate, we can get minus 4 into 10 to the power of minus 3. Then we can get 4 by 40. 4 by 40 is 0.1, that is 0.1 milliseconds. Clear? This is question number 5. Only circuits are changing here. This model of questions are already framed in GATE exam for 2 marks. Clear? Only in the previous problem and this problem, the concept is same. What it is changing here? Only circuit is changing. According to circuit, we can apply KCL and KVL. The concept is same. Then you find the minimum gate pulse width. If you want to minimum gate pulse width means corresponding to which current you are calculating? Latching current. Corresponding to latching current we are calculating. Clear? See the based on same topic. See the another question, that is question number 6. Okay. The circuit shown in figure. This is question number 6. The circuit shown in figure. Latching current equal to 50 milliampere. Holding current equal to 20 milliampere. To ensure reliable turn on, minimum gate pulse width is 50 microseconds. Then resistance R equal to dash. See the question number 6. Parallel ga వెళ్ళిపోతుంది, స్లోగా చెప్తున్నాను కాబట్టి. Yes. See the question number 6. The circuit shown in figure. Latching current equal to 50 milliampere. Holding current equal to 20 milliampere. To ensure reliable turn on, minimum gate pulse width is 50 microseconds. Then the resistance R equal to dash. Okay. See the figure. This is question number 6. Okay. Given that latching current equal to 50 milliamperes. But the holding current 20 milliamperes. Minimum gate pulse width is given. What is the minimum gate pulse width? Minimum gate pulse width. Minimum gate pulse width is 50 microseconds. This is the given circuit. This is 100 volts thyristor. It's 20 ohms, 200 millihenry. 20 ohms, 200 millihenry. Then this is resistance. This is a given circuit. Okay. Yes. This 20 ohms, 200 millihenry. Resistance, supply is 100 volts. See the difference in the previous problem and this problem. In the previous problem, the resistance also given. You calculate what is the minimum gate pulse width. But in this problem, minimum gate pulse width is given. Then you calculate what is the resistance. Same concept, and circuit is also same. Okay. Then you see. Then how to write the formula? Then latching current equal to. This is RL circuit na, excited with DC supply na. Then how to write? 100 by 20. 1 minus e power minus resistance. Resistance is how much? 20. Inductance is how much? 200 millihenry. 200 into 10 to the power of minus 3 into T. Plus. You want to find resistance. That is 100 by R. What is the latching current? The latching current is equal to 50 milliampere. that is 50 into 10 to the power of minus 3 is equal to 5 into 1 minus e power. This how much you get? That is minus 100t. This if we simplify this 100t, that is 100 by R. Then 50 into 10 to the power of minus 3 is equal to 5 into 1 minus e power minus 100. T is given 50 microseconds, 10 to the power of minus 6 plus 100 by R. Then we simplify this. Then from this, what you can get? R equal to 4 kilovolts. Clear? This model also already framed in GATE exam for 2 marks. See, this is model is repeated, only circuit is changing. That previous question also, that model also previous GATE question, and this model, even though question is not same, but this model is already framed in GATE. But concept we are applying is same, but only circuit is changed. That answer depends on your calculation only. Clear? Based on mathematical calculation that we are doing. R equal 4. Yes. Concentrate. Okay. Then based on this topic, then based on characteristics and modes of operation, see the last model of question, that is 7th question, that is given in workbook. Yes. Question number 7. The latching current for an SCR inserted in between a DC voltage source of 200 volts and the load is 100 milliamperes. Compute the minimum width of gate pulse current required to turn on this SCR in case the load consists of 2 millihenry. Second one, that is B. R equal to 20 ohms in series with L equal to 2 millihenry. C. R equal 20 ohms in series with L equal to 20 millihenry. Say this one. A thyristor is connected. A thyristor is connected in between a DC source voltage of a DC source voltage of in between a DC source voltage of that I given 200 volts, a DC source voltage of 200 volts. Okay. Then L is in the first case. This is some load. This is load, connected between load. And this current is given as 100 milliamperes. This current is given as 100 milliamperes. Yes. In this load, the first one is, if L equal to how much? 2 millihenry. L equal to 2 millihenry. Second one is, second problem. If L equal to 2 millihenry and R equal to 20 ohms in series, that is R equal to 20 ohms, L equal to 2 millihenry in series. L equal to 2 millihenry in series. In the third case is R equal to 20 ohms, L equal to 20 millihenry. This is first one. If it is connected, what is the minimum gate pulse width? If it is connected, what is the minimum gate pulse width? If it is connected, what is the minimum gate pulse width? That you want to calculate. 3 questions you want to solve here. Okay? See the first one. First one. If L equal to 2 millihenry, if the load is 2 millihenry, then what is the minimum gate pulse width? If L equal to 2 millihenry means we are connecting with L equal to 2 millihenry, a thyristor with inductance of 2 millihenry. Okay, the supply voltage is 200 volts. What this current is given? This current is taken as a latching current, 100 milliampere. Okay, then in this case, you know that VL equal to L into di by dt. Then V by L equal to, that is VL by L equal to di by dt. Then from this, what is di equal to? VL by L into T. Then what you take? I equal to VL by L into dt. Then integrate. What you get? Integral di equal to VL by L into integral dt. Then this is IL equal to VL by L into T. That you want to calculate what is the, if L is how much it is given? 2 millihenry. L is 2 millihenry. IL is how much? Latching current? 100 milliampere. 100 into 10 to the power of minus 3. VL is how much? 200 by L is how much? 2 millihenry into T. Now from this, what the T you can get, you tell me? Yes. This we can get how much T we can get? That is 200 into 10 to the power of minus 6 by 200. Yes. This is 100. This is 200. This we can get. From this, what is the T you can calculate. That is the minimum gate pulse width required for reliable turn on of the SCR. For reliable turn on of the SCR. Okay. For example, if you take this is 40 milliampere, that is 40 into 10 to the power of minus 3, and this is 100, and this is 2 millihenry you take. This is 100. This is 2 millihenry you can take. This is 40 milliamperes means then sorry, one small change here. This you take 100 volts and this you take 40 milliamp in the problem. You want to change that one. This is 40 milliamperes. Okay. This latching current I am changing to 40 milliamperes. This is 100 volts. Then here 40 milliamperes. This is how much? 100 volts. If you take this is 200 volts, as it is 200 volts. This also 200 volts. Sorry. Okay. Then from this, what the T you can get? Okay. This is 80 into 10 to the power of minus 6. That is 80 into 10 to the power of minus 6 by 200. Then what is T you can get? 0.4 microseconds. Clear? Small. The given supply voltage as it is 200 volts, but you take latching current is 40 milliamperes in the problem. Okay, latching current is 40 milliamperes. Then this L equal to 2 millihenry. Then how much minimum gate pulse width is required for reliable turn on? 0.4 microseconds is required. This is the first case. You concentrate on second one. B. Is clear? If R and L, this is R equal to 20 ohms, L equal to 2 millihenry is connected in series. Same circuit. This is as it is 200 volts, as it is 200 volts. Then thyristor, connected with thyristor. R equal to 20 ohms and L equal to 2 millihenry. This is R equal to 20 ohms and L equal to 2 millihenry. Then in this case, what is the minimum gate pulse width? You tell me. Same. Given. Then IL equal to V by R into 1 minus E power minus R by L into T. Yes. What is the latching current? As it is 40 milliamperes. Latching current is 40 milliamperes. Supply voltage is 200. That is 200 by 20. 1 minus E power minus R. R is 20. L is 2 millihenry into T. Then if you solve this, we can get T equal to 0.008 microseconds. This is the minimum gate pulse width required for reliable turn on of the SCR. If it is connected 20 ohms and 2 milliamps. Then third one, concentrate on C. Yes. Given that same a thyristor, supply voltage is 200 volts. Supply voltage is 200 volts. Instead, here it is connected 20 ohms as it is. But instead of 2 millihenry, you taken the inductance is 20 millihenry. For same value of latching current, that latching current is 40 milliampere. The latching current is 40 milliampere. Okay. If you connected latching current is 40 milliampere as it is, but you are increasing the inductance to 20 millihenry. Okay. Now same. What you can write formula? 200. That is latching current. Latching current is how much? 40 milliamperes is equal to 200 by 20. 1 minus E power minus R. 20 by 20 into 10 to the power of minus 3 into T. E power minus R by L into T. This is 2 into 10 to the power of minus 3, where you have taken 20 into 10 to the power of minus 3. Then if we calculate T here, we can get T equal to 4.008 microseconds. Okay, this is the problem. If only inductance is connected with a 2 millihenry, we are getting the minimum gate pulse width for reliable turn on is 0.4 microseconds. If R and L is connected, that is R is 20 ohms, L equal to millihenry, then we are getting the minimum gate pulse width for reliable turn on is 0.4008 microseconds. If we are connected R equal to 20 ohms and L equal 20 millihenry, we are getting the T equal to 4.008 microseconds. Okay, clear? Concentrate on this. This is A and this is B and this is C. That simplification you do. And this simplification, mathematical analysis only, that you calculate using calculator. But based on this problem, I want to make one observation that is important for theory question. See, what is the observation? I want to explain based on this question number 7. Okay. Based on this one, what is the observation? Based on this problem, I want to explain one observation. Based on question number 7, see the observation. For same supply voltage, if L equal to 2 millihenry, the minimum gate pulse width for reliable turn on of SCR is 0.4 microseconds. Next, for same supply voltage, if L equal to 2 millihenry, R equal to 20 ohms, we are getting the minimum gate pulse width is 0.4008 microseconds. Yes, next. For same supply voltage, if L equal to 20 millihenry and R equal to 20 ohms, we are getting the minimum gate pulse width is 4.008 microseconds. Yes, 4.008 microseconds we are getting. Now see the observation. Here 2 millihenry, this is the minimum gate pulse width. This 2 millihenry and 20 ohms, this is the minimum gate pulse width. That means even though resistance is added, the effect of resistance on the gate pulse width is nothing but a gate on time is negligible. Clear? Even though resistance is added, the effect of gate pulse width or gate on time is negligible. This is 0.4 microseconds. Nearly it is also equal to 0.4 microseconds. But see the comparison. Same resistance, but I am increasing inductance instead of 2 millihenry to 20 millihenry. Now what is the term? What is the minimum gate pulse width is required? 4.008 microseconds. It is increased by 10 times. It is increased but we cannot say that exactly it is a 10 times. Okay, but the inductance effect is there. That's why if the inductance is increases, the gate on time for reliable turn on must be increases. That means you connect the gate for more time or less time. Then we connect the gate must be connected for more time. Then only that SCR will be turned on. This is very important. That is, one observation is the effect of resistance on the gate on time is negligible. The effect of resistance on gate on time, that is gate pulse width is negligible. It is independent of the resistance. Second observation, if L is increases, gate pulse width is, that is, if inductance is increases, if the load inductance is increases, then minimum gate pulse width is also increases. Minimum gate pulse width is also increases for reliable turn on of the SCR. These two important observations. Gate pulse width, that is the effect of resistance on gate on time or gate pulse width is negligible. But if inductance is increases, minimum gate pulse width is also increases. For reliable turn on of the SCR. That means if the load inductance is increases, we can connect the gate for more time for reliable turn on. Gate is connected for more time. This is the observation based on this problem. Okay, this comes under topic 1. This is the classroom workbook question that I discussed. This maximum I discussed here problems only. If any theory questions are given based on this concept, then whatever the concept I discussed and whatever the points I list out, based on that point we can answer any theory questions based on this topic. But this model of problems are enough based on this concept, that is you concentrate. Okay. But if any theory questions are framed, that concept based whatever the points I list out now in the discussion of topic, that you concentrate. Okay. This about one concept based on construction, static VI characteristics and modes of operation. This is the model of questions important. All these models already framed in all the competitive exams, either GATE or IES. Okay. Then in thyristor itself, we go for another concept, okay, that I want to discuss. We go for the I given construction, static VI characteristics and modes of operation. Then you go for the another concept in the case of thyristor, that is nothing but what are the different turn-on methods of SCR. That is. In the chapter 2 itself, the second one is that is thyristor concept only. Based on this thyristor, the another concept I want to discuss is what are the different turn-on methods of SCR. You see, what is the turn-on methods of SCR? Turn-on methods of SCR. This is another concept in thyristor. What do you mean by turn-on of SCR? You tell me. What do you mean by turn-on of SCR? Yes. Turn-on is nothing but bringing the SCR from the forward blocking mode to forward conduction mode. Turn-on is nothing but bringing the SCR from the forward blocking mode to forward conduction mode. Bringing the SCR from forward blocking mode to which one? Forward conduction mode. Yes. To bring the SCR from the forward blocking mode to forward conduction mode, so many methods are there. Then what are the methods we are employing to bring the SCR from the forward blocking mode to forward conduction mode? Okay. To bring the SCR from the forward blocking mode to forward conduction mode, then one is we can apply forward voltage triggering method. Forward voltage triggering. Okay. Forward voltage triggering method. Another one is gate triggering method. Gate triggering. Gate triggering. Third one is temperature triggering or thermal triggering. Temperature triggering or thermal triggering. Temperature triggering or thermal triggering. Fourth one is light triggering method. Light triggering. Then fifth one is dV by dt triggering method. dV by dt triggering. These are the methods we can employ in order to bring the SCR from the forward blocking mode to forward conduction mode. Forward voltage triggering, gate triggering, temperature triggering, light triggering and dV by dt triggering. Then what do you mean by forward voltage triggering? This method I already explained. Applying forward breakdown voltage. Applying forward breakdown voltage. Applying forward breakdown voltage. Applying forward breakdown voltage. And bringing the SCR into forward conduction mode is called forward breakdown, that is forward voltage triggering. Applying forward breakdown voltage and bringing the SCR into forward conduction mode is called forward voltage triggering, but practically not preferable. The reason I told, SCR may be damaged. Practically not preferable. The reason I told, SCR may be damaged. Okay. The next one is gate triggering, temperature triggering, light triggering, and dV by dt triggering. I already given some introduction to gate triggering. If the gate is connected to the SCR, what happens? That concept I already given some introduction. But in detail, mainly this gate triggering and temperature triggering, mainly I want to explain using two transistor analysis of SCR. That means practically SCR is equivalent to connection of a two transistor. First I want to discuss that concept. After discussing that concept, using that one basic equation, these two methods can be explained. Gate triggering method and temperature triggering method. Not only these two methods, then by using the two transistor analysis, I also prove that SCR is within the SCR a positive feedback action is takes place. I told already, SCR is a positive feedback device. Within the SCR, how the positive feedback action is takes place, that can also be explained by using two transistor analysis. That means to explain this gate triggering method and temperature triggering method, first I want to explain what exactly two transistor analysis. Then explaining the two transistor analysis using these two methods, then I go for light triggering and dV by dt triggering. Now we'll see the concept of first two transistor analysis. These are the methods we can use for triggering. That is turn on. Then what exactly two transistor analysis? From that how you can explain these methods, that you will see.